which tells us what exact algorithm will be used to choose between multiple profile entries available to us. So one way to do it, kind of actually a fairly simple way, but gives you fairly good results. You can calculate a hash based on certain number of fields in the packet, and then they do it like modulo 3, for example, in this case, and then send to one of the ports. It will actually provide you, if your hash is fairly big, it can provide you a fairly decent distribution. It will almost look like equal. Okay. So that's what's happening here. So I just kind of continue the code here. So this is ECMP hash. What it does, it takes those fields, IPv4 source address, destination address, protocol, so our typical 5 tuple, and calculates CRC16 on top of those fields. So what that means, it allows us to separate traffic, but it also guarantees that as long as the traffic belongs to the same flow, so same host, same protocol, same source and destination port, it will go onto the same link. So there will be no problems with packet reordering or anything like that. Okay? And then as long as this bit width is, say, probably 6 bits or above, right? We have a situation if it's really small, like in the older systems, what they used to do, they would used to take, like, for example, 8-bit or 3 bits, XOR them together, and then just do modulo 3. It would provide a really bad distribution because you had like you would typically have a situation when it's not power of 2. You would have things like flow number 0 goes here, 1, 2, 3, 4, 5, 6, 7, and this will be always underutilized. If you have a big number, say it's 6 bits or more, right? So when we do 64 divided by 3, then what we see is that basically here you'll have 21 flows, maybe 22 flows. So the error is not that big. If you use more than 6 bits, like 8 or 12, you almost will not see the distribution will be quite even. Okay? And then, of course, there are a lot of other algorithms that people can use to do ECMP. And from the P4 language standpoint, it's only a matter of, you know, being able to specify certain attributes here that maybe you don't want, like a selection key to be a hash, but you want a special selector which performs, for example, dynamic load balancing or resilient hash or anything of that sort. And I can talk a lot about those, but that's not kind of the point of our class, I think. So, any questions on action profiles? So the main idea is that the entry itself does not contain the actions. The actions are contained in a separate table, the profile table. And so there could be either one action or multiple. And if it's multiple actions, then you have to have a selector to choose between those. Okay, so now we go to the most interesting piece, is the control flow. And that's quite easy. So there are not that many statements that you have to learn because we don't have loops, anything like that. So the main thing that you need to do is to use a keyword apply, which means perform a lookup in the table and execute the actions on the match. So the semantics here is always of sequential execution. And again, the compiler, based on the target, should be able to parallelize this and you know, if you have a good target, the compiler can do a very, very good job. So right now in P4, there are two standard control flow functions. There's ingress, which represents the ingress pipeline, and then there is egress. So here's how the code looks like. So this is a typical thing that you can do. For example, we use if statement to do two separate processing paths. One is for IPv4, another one is for IPv6. So all this process are functions, control functions, which effectively what they do, they just, you know, apply a table with a similar name. Again, based on the target, those if statements can be more complex, less complex. There can be a certain number of those. But the important thing is that this program executes at the, using a, you know, very deterministically. So there is only a certain time that it takes to execute it. By the way, I forgot, we probably didn't turn this on.
Did you turn this on, Josh?
I turned it on like,
Okay.
yeah.
You did.
Oh!
I mean, you should double check to make sure I did it right. Yeah, I turned it on when I walked through this a couple months ago.
Okay. So when we use the apply statement, there are a couple of important variations of it that can be used to either express your program better or just allow us to do better optimizations as well. So after the apply, you can have a special select block. So here, the select block contains a special keyword called miss, and that's what we'll need to do if there is a miss in this table. So what we're doing here is actually a very simple thing. First, we perform a lookup in the IPv4 host table. So we perform a lookup based on the exact IP address. Remember, that was the first table I was showing you. If there is a miss, where do we need to go? We need to go to the routing table where we can do a longest prefix match. And that's exactly what we do here. So that's a very typical construct. The other one you can do is you can do an action branching. So imagine that you have a table where we can decide based on the destination MAC address whether we want to perform IPv4 or IPv6 processing or say MPLS, ECAP, and so on and so forth. So normally how this is done in the real system, the packet comes in, if it contains what we call my MAC address as a destination, then we perform a certain action like send the packet to the IP stack. So this is a generalization of that. So here's the table. It will match the packet based on the destination MAC address, the broadcast domain, and the source port. And we can use ternary matching. It's very convenient so that you can, for example, have one MAC address regardless of your VLAN and so on. And here are some actions that we can execute: enable IPv4 lookup, IPv6, and so on. So here's what I can do in the control path. I can apply this table, say apply router MAC, and then the select clause tells me if the action that was chosen is enable IPv4 lookup, then go this way. If it was IPv6 lookup, go this way. It's like a case statement, but there is a very important reason why we do that. The thing is that in the real hardware, the match and the execution of the action are typically separated in time. So if you look really kind of closely, you will see that the first match happens, right? And even on the software, right? And then you chose the action, and then you go and start doing all those things, right? So that means that we can potentially start processing the tables inside those functions earlier, before we actually have a chance to complete the execution of those actions. Similar, by the way, similar thing was with the miss as well, right? So, and that allows us to use parallelism in the real devices much better.